Hi everyone, welcome to this session BP1270, how to optimize cloud cost and increase resiliency for stateful applications with SUSE Rancher. That was a long title, but long story short, we're going to be talking about three main topics. First, RKE2 and SUSE Rancher. So RKE2 as a Kubernetes distribution. And then we're going to take a look at stateful application in Kubernetes, why they are so particular, what are their requirements, constraints, and how to run them in the best possible way in the cloud. And there's the last component of this talk is going to be focused around storage and data services you can have on top of those stateful applications, because, well, stateful applications are usually mission critical applications. So you need to really take care of them and make sure they are highly available in the cloud. And finally, we'll close with a demo of the different solution and component we're going to be talking about today. So let's get started. My name is Nick. I'm a principal developer advocate with Ondat. I've been working with Kubernetes for the past 6 years across different companies. So at Cisco, working mostly on the CNI or container network interface, and now focusing on data services and distributed storage for Kubernetes. So for our first topic, let's take a look into RKE2. Hopefully most of you are already familiar with SUSE Rancher. If not, SUSE Rancher is a Kubernetes management solution completely centralized that allows you to deploy Kubernetes cluster anywhere in any environment, whether it's on premises or in the cloud. And it also allows you to manage Kubernetes operation in a very streamlined and optimized way in terms of upgrade, in terms of security, applying best practices, etc., etc. It does support multiple deployment model, so unmanaged and managed, as well as multiple Kubernetes distribution, whether vanilla Kubernetes, upstream Kubernetes, or RKE and RKE2, which are SUSE Rancher own Kubernetes distribution. In terms of the deployment model, so SUSE Rancher allows you to deploy Kubernetes as unmanaged or managed from a cloud provider perspective. That means that when you deploy an unmanaged cluster, as in the cloud provider or on premises, it means that as a platform admin, you're responsible for the infrastructure component as well as for the Kubernetes software layer. So typically it means that you are going to upgrade the nodes yourself, the control plane nodes, as well as the worker nodes. And in that particular case, of course, when you're running SUSE Rancher, Rancher is going to manage this for you. So the second one is managed Kubernetes. So typically this is cloud provider particular offering like AWS EKS or Google GKE, where you don't manage the node installation yourself and you don't have access to the control plane nodes. They are deployed by the cloud provider in their environment, typically in a dedicated VPC. So it's not part of the infrastructure that you manage as a platform admin. So it does have cost involvements in this. So typically in a managed environment, the control plane will be deploying nodes into EC2 or into GC for Google. So you will have to pay at first for those resources. So the compute resources, whether unmanaged or managed, you have to pay for the EC2 instances. When it's managed, then you're going to pay for the fact that the cloud provider is giving you this curated platform. So you're going to add those costs on top of it. And with that said, why would you run RKE2 as opposed to a managed Kubernetes environment, you may ask? Well, RKE2 is the next generation Kubernetes engine that has been designed for more security. And typically the second name for RKE2 is also RKE government. And so there's couple of features that makes it extra secure. So it's a distribution that can pass the CIS 1.5 and 1.6 benchmarks. So to run in a security sensitive environment or any enterprise environment, I would say it's a very good baseline. As I said, it's upstream conformant Kubernetes distribution, and it does have extra features such as Cilium and Multus as CNI. You can install it in air-gapped environments, so without connection to the internet. By default, Docker has been replaced by Containerd, which is already a good start because Docker Shim has been deprecated not so long ago. It has compliance with FIPS 140-2, which is a standard to approve cryptographic modules. And finally, it has all the benefits of RKE1 in terms of the Kubernetes conformance, as well as K3S because it's a single binary. So it's very easy to install from the Rancher server or manually by just deploying the binary and running this binary with a couple of options and just joining the nodes to the cluster. So a lot easier than deploying Kubernetes yourself. And I would say compared to a curated cloud provider solution, well, this one is cloud agnostic. You can run it anywhere, whether it's on premises, a gapped environment, or in public cloud providers environment. Another benefit is that SUSE Rancher gives you this ability to very easily deploy applications using Helm charts, but not the CLI, just using simply the UI. In terms of user experience, the workflow is quite easy. You just look for the application you want to install and then fill up the different fields, click install, and then the Helm chart will be deployed for you. And in the same way, when the application vendor deploys or creates a new version, release a new version of the application, it's very easy to upgrade it with a couple of clicks, and again from a single centralized place. Where it's going to play a role for us today is that obviously any kind of software can be installed this way, whether it's developer-focused application or tooling, or infrastructure applications such as data services, right? And for example, today we're going to be using Ondat as the underlying solution to provide these extra data services on top of Rancher, but really can be anything. So the point of this first section is really to show you that with Rancher, first, it's really easy to deploy Kubernetes, and second, it's also very easy to deploy and manage application, including infrastructure application, that is required to run stateful application in Kubernetes, because we're going to see what kind of challenges they face and how to alleviate them. But before talking about this, let's address this first topic. Stateless versus stateful application, especially in the context of Kubernetes. What does that mean exactly? Well, first, no application is entirely stateless. You may have stateless component, but under, with some sort of form, you need to persist data or, cache or messages into disk at some point for every single application. And the second statement is that, of course, with the advent of microservices, every development team is now responsible for the entire microservice. And each of these microservices typically come with its own data or its own message bus, database, test workflow, CI pipelines, and pipelines, if they are done in a Kubernetes way with tools like Tekton, then this is where you may need some extra data services as well. So now let's try to figure out the differences or the technical differences between stateless and stateful components or workloads in Kubernetes. So when looking at this picture, you can see first that they are managed by different controller. Stateless applications or stateless workloads in Kubernetes are typically managed by deployment controller, and stateful applications are managed by stateful controllers. That's the first difference, obviously. Then in terms of the service that you build on top of the workload, so typically a load balancer service that will redirect the request towards one of the pods, then stateless needs a normal service. So typically a cluster IP as opposed to stateful workloads. So a stateful set will tell you or will mandate the creation of a headless service, meaning that when your request, you trigger a DNS request against that particular service, the headless service is not going to return, it's not going to reply with a single IP address in a random fashion. It's going to list all the IPs of that particular service. So all the IPs of the pods composing the headless service. Then in terms of the storage, there are quite a few differences. When you create a deployment within the manifest, you can only specify a single PVC or persistent volume claim, meaning that all the pods that are defined as part of that particular deployment will get access to the same persistent volume claim or to the same backend storage. Multiple pods accessing the same backend storage mean two things, right? Either if it's a read-write once type of access, only the first pod would be able to access the PVC, and it would be local to the specific node where that pod is running. Or if it's a read-write many, then that's fine, because typically this will be an NFS shares, and all pods from that deployment will access and can write and read data onto that particular NFS share. If you are running a stateful application, it means that typically if it's a database, you don't want to run your database on an NFS share on a network device, because the performance are going to be ridiculous, right? The performance are going to be super, super low. So you want to access performance storage for a stateful application like a database or message bus. And for this, stateful set has a special component or a special field that is called a persistent volume or volume claim template. And that definition will allow you to create one PVC per pod. So you just specify a template, and for every stateful pod, the controller will create one individual PVC and attach it to that pod. That means that if you want to create a database cluster, then every node from that cluster will be able to have its dedicated storage disk and storage space. Another important difference between stateful pods and stateless pods is that stateful pods have a predictable ordinal number that is going to be incremented every time you create a new pod. So for example, if you have a MongoDB cluster, then the first pod is going to be called maybe MongoDB 0, then the second one MongoDB 1, etc., etc. And if one of those pods get deleted manually or by Kubernetes, then another pod with exactly the same name will be created. It will have a different IP address, but from an identity perspective, which is managed by DNS in Kubernetes, it will be exactly the same. Stateless pods, usually they have super random prefixes. If you delete one pod, a new one will be created, not with the same ID. And it's very useful for stateful pods, because obviously if you delete a pod and it has a persistent volume attached to it, then you don't want to lose your data, right? So the persistent volume will stay there, another pod with the same identity will be created, and the same volume will be attached, right? Which does have a couple of consequences that we're going to touch upon in the next slide. And finally, the last difference is how you perform operations on stateful workloads as opposed to stateless workloads. When you are doing rolling updates for deployment, the process is going to be different from when you are doing it for a stateful set. And over time, Kubernetes has caught up in terms of these abilities, and now you can easily update stateful sets in the same way you can easily update deployments. One component is missing though into this picture, which is the storage class, and typically this is what is used by cloud providers or even on premises or by Rancher or SUSE Rancher. The storage class allows you to plug in a CSI, which I'm going to mention next, that adds a couple of extra features on top of PVC or bare PVC and persistent volume. So it allows you to dynamically provision the persistent volumes, the backend volumes, the backend storage, as new persistent volume claims are created. So the typical workflow without dynamic provisioning is to first create the PVC, then PVs, and attach them together through a storage class. But when you have a dynamic provisioning enabled for your storage class, then as soon as you create the PVC, the corresponding PV is created without you having to take care of it. Now, on the storage class level, this is where you want to specify extra services or data services if they are available and managed by feature labels. So adding labels onto the storage class manifest. So typically you want things like replication, encryption, compression, caching, thin provisioning, all those type of things. But guess what? They are not available by default in Kubernetes. Kubernetes alone won't provide these features. Okay, so now in terms of the stateful application challenges, there are a couple of them, right? So when a node fails, and assuming we have a read-write once type of volume, what happens? Well, if you have the PVC that is attached locally, the node fails. Typically after 5 minutes, you will have to tell Kubernetes, kill that pod, right? Because I want to restart it somewhere else. But when the control plane is going to try to restart the pod, it won't be able to do it because the volume is not available anymore. Remember, the volume is local and by default it's not replicated. So this is one challenge, like what happens when the node fails? Of course, if it's a highly available application, you have the redundancy, the high availability at the application level, but still you are running in a degraded mode, meaning that you will have to manage this situation manually. And while you are doing it, you have less availability for your application. And when you create your new pod, potentially data need to be synchronized. So there's a lot of manual actions that needs to happen there, potentially with their own set of errors or eventual errors and problems. If you have data that is replicated at the Kubernetes layer, then it would be a lot easier. So the persistent pod cannot be restarted on the remaining nodes with the volume attached. And also, if we are assuming that you are running your stateful pod in the cloud in a particular region and availability zone, probably you already know that EBS volume, for example, can be attached to different nodes in a single availability zone. So if you have node failure or one node failure in an availability zone, you can attach your disk, your volumes to another node within that availability zone. But as you've probably noticed over time, you can have a full AZ failure. In that particular case, well, EBS volume cannot be easily switched to another availability zone. You need to restore from a snapshot, and potentially, you will have downtime. So again, if you have Kube native data services happening on top of that, you can alleviate those issues. So what I mean by data services, so those are things like replication with SUSE Rancher Longhorn, for example, you can see here, or with Ondat, which provides also additional data services. And these services are available through the CSI driver or container storage interface, which is an interface defining standard to plug in your backend storage. So previously, all the different type of vendor were directly integrated into the core Kubernetes code, which we call in-tree. Now, this support has been removed for a more pluggable approach where every vendor is responsible to provide its own CSI, and Kubernetes is just expecting a couple of functions to be available and standard APIs available from the CSI driver. So typically those RPCs are things around dynamic provisioning and deprovisioning of a volume that the vendors need to accommodate, attaching or detaching a volume from a node, mounting and mounting a volume from a node, functions related to snapshot, and also related to provisioning a new volume from a snapshot. Now, on top of these basic services that are expected by Kubernetes, it's up to the vendor to provide additional features. And those features are, again, installable by using Helm, because, well, the CSI driver is just another application that you install on top of Kubernetes, right? Which makes it very easy to manage with SUSE Rancher and the Helm chart I've mentioned before, the catalog from the UI. So what kind of data services you would need to run stateful sets in Kubernetes the best possible way? First, in terms of availability, right? You want the ability to distribute volume replica in different failure domains. Remember when I was mentioning, different availability zones so that you can fail over from one AZ to another AZ. So having the ability to be topology aware, automatic volume failover so that when a node fails, another replica is promoted and the pod is forcefully removed from the control, or terminated from the control plane perspective, so that it can be restarted on another node, and the pod will find its existing volume because a new replica will have been promoted. So of course you need synchronous replication. Volume remote access may be another one when you have the replica that has been promoted on one node and maybe the pod has been scheduled on another node. This is less ideal, but still, if it allows you to increase your availability, well, that's a good feature to have. Then in terms of performance, you have maybe the requirements for SSDs or NVMe, and you may want to group those disks into a set of nodes as opposed to distribute them into all nodes. So those two architectures are hyper-converged. Every node is participated into the storage capacity, or centralized. A couple of nodes will host all the storage, all the performant SSDs and NVMe should be available. In terms of recoverability, then of course you need features such as snapshot, backup, and ability to restore, application consistency, with the ability to quiesce the file system or the database, and eventually also export to cloud object storage your data, basically. Manageability, well, typically you don't want the synchronization between the replica to take hours, because if you have a failure and you need the data to converge quickly, then you need a fast synchronization. Compression, thin provisioning are, typically something that you can find on any type of storage array. So you want to find them as well into your Kubernetes environment if you want to run the same application as before. If you're running your mission critical application on a very expensive SAN or storage array, you want the same feature when migrating to cloud and to Kubernetes, right? And then security, right? This is very important, especially when going into the cloud or adopting a multi-cloud strategy. No single cloud provider can guarantee end-to-end encryption. So you need encryption at rest, you need encryption in transit with TLS, you need a proper key management system that is eventually not hosted in the cloud. If the cloud provider encrypts your data, but also provides you the store for the keys, it means that it has access to these keys. So security is not at the top level, let's say. In this last part, we're going to take a look at storage costs in the cloud, in particular when running stateful workloads in Kubernetes. So storage is probably one of the most important source of expenses when you're scaling your applications. If we take the example of AWS, and it's also the case with any cloud provider out there, there are two types of storage. In AWS, it's called the instant store, which is the local storage attached to your machine that is physically attached to it. This storage is typically ephemeral, meaning that when you shut down a node and reboot that node, the data that was sitting there is completely wiped out, which is not what you want. Typically, those drives are HDD, so spinning disk, can be NVMEs, can be SSDs, but it's part of the EC2 instance hourly costs, which mean that it's quite cheap compared to the other type of storage, which are the typical, network, still block devices, but network attached storage to your instances. So obviously there's a plethora of options for EBS volume in AWS, GP2, GP3, provision IOPS if you want more performance, and the more performance, the more cost compared to your local NVMe drives, although your local NVMe drives is an order of magnitude superior to EBS drives in terms of performance. But if you think about it, well, data services in Kubernetes, in particular, synchronous replication, can help using instant store, right? Because of course you need safeguards to avoid a Kubernetes node to be shut down and rebooted. But when it happens, it's not that dramatic, because then you will have the replication that will be there, and so the solution will fail over to a new node with the replica already available, so the pods will be restarted. That's a good way to save money for storage. So effectively, we've shown that data services can help bridge the gap here. And before concluding, let's jump to a very quick demo. So there's just a couple of things I want to show you here, and how easy it is to deploy and manage these data services with Rancher. So first, when you deploy your Kubernetes cluster here, this is EKS, you have the possibility to add custom user data or cloud init config when you bootstrap your Kubernetes cluster. In that particular case, I've mounted dev NVMe 0 and 1, which is the local instance store drive, into a particular directory that is available for the Storage OS engine to consume and start writing data and doing replication. So by just launching this script, you don't have to do anything else but just install Storage OS with Helm, which is really easy, as we've said, we've seen earlier. And once Storage OS and Ondat is installed, the only thing you need to do really is create a storage class. Here I've created a storage class with replication enabled 2 replicas should be deployed every time. Topology aware enable, which means that I can create replica across multiple availability zone, and also encryption at rest. So now if I create a PVC here, I can see that it inherits the property of that storage class because it's using that storage class. And now I can see a new secret, which is the private key used to encrypt that particular volume. That concludes our session for today. I hope you enjoyed it and that you learned something. Before leaving, just a couple of key takeaways for today. We've seen that SUSE Rancher acts as a common cloud-agnostic Kubernetes distribution and management layer that dramatically simplifies Kubernetes management and operations. And we also seen that Kubernetes is ready to run your mission-critical stateful application with cloud-native data, provided that you can reach the right level of availability, scale, and performance. And finally, persistent storage challenges are not addressed by default. This is an area where you really need to pick the right solution that suits your requirement. I hope you enjoy the rest of the conference. Take care of yourself. I hope to see you soon. Bye-bye.